Boom! All right, folks, you here again. How are you going? So we're on the big board, and we're here because we want to talk about trigonometry. All right, and we want to talk about trigonometry beyond the right angle triangle. So it is probably an appropriate coincidence of symbolism that we go in beyond the right angle triangle and we're using the big board, because as you could already guess, we have a lot more to talk about, all right, than just the regular sine and cosine and tangent, opposite over hypotenuse, opposite over adjacent, adjacent over hypotenuse, right? Pythagoras theorem, etc., etc. Hypotenuse squared is equal to opposite squared over adjacent squared. If you're here to watch this video, then chances are you are already familiar with those things. So we want to go a little beyond that now. We want to get into the realm where we're dealing with angles greater than 90 degrees. Or we're dealing with angles that might be 90 degrees at all. So in other words, instead of just the right angle triangle, which you already know, we want to deal with triangles that are not right angle triangles. Your scalene triangle, right? And then within the scalene, you have other little things. So for example, this here is what we refer to as an acute triangle, where all the angles in the triangle are less than 90 degrees, right? This here is what we refer to as an obtuse triangle, where the largest angle is greater than 90 degrees, and of course it means that the other remaining two angles will be less than 90 degrees. So using 90 degrees as a reference point out of familiarity, we can get two other general classes of triangle, the acute and the obtuse. We will look at specific cases of both. Yeah? All right, so let us get into the sine rule for starters. This video is dedicated only to the sine rule. We'll do a separate video for the cosine rule. All right, so let me do a little reading here, and I want you to take some notes if you have to. I'll read it out. I'll read it twice. Of course, if you're watching the video, you'll always have the opportunity to rewind and write over. So the law of sines, commonly known as the sine rule, says that the ratio of the length of a side of a triangle to the sine of the angle opposite that side is the same for all sides and angles in a given triangle. Let me read that again. I read it slower this time. The law of sines, or the sine rule in brackets, says that the ratio of the length of a side of a triangle to the sine of the angle opposite that side is the same for all sides and angles in a given triangle. Now it's sounding like plenty, yeah? It's sounding like some great Pythagorean thesis or something, right? But it's not as complicated as it sounds, right? And I want to take a moment just to encourage folks who are getting into this topic for the very first time. Try not to go into this telling yourself that it's hard. The understanding of the concept is not as difficult as it seems, and once you understand the concept, then the only issue after that is just the algebra. Of course, we know sometimes people are at different levels with the algebra, but if you're already familiar with your trig ratios from the right angle triangle, then we're just taking it a step further. That's all, right? And before I go further, I want to make the point that angles greater than 90 degrees also have values for the trigonometric ratios. All right? So even though we work up to here, up to this point, in terms of your maths journey, understand that sine 91 is a real thing. 91 degrees has a sine, 105 degrees has a sine, 120 degrees has a cosine, it also has a tangent, it also has a sine. All right? So again, I'm just making the point that we expanded, right? This here is something that you could easily visualize. So you know, for example, that the sine of 53.1 degrees is this length over this length. We'll get into the actual values in a little bit. If I ask you now to visualize the sine of 120 degrees, how are you doing that? Right? The visualization of the sine of this, or the cosine of this, or the tangent of this, that is a little beyond what we're doing here today. Right? Students who do add maths are the ones who will actually start to get into that. And even there, it's kind of a little tricky. Right? Yes, some things easier to visualize than others. So what I want you all to do going forward is just to accept the fact that angles greater than 90 degrees have associated trig ratios as well. Even if you can't visualize it. Sometimes that is how it is in maths, and sometimes that is how it is in life too. Sometimes you accept something and you go with it even though you don't see it, even though you don't understand it. Right? People in the Christian religion talk about walking by faith and not by sight. There is a certain level of that in mathematics as well. Right? And I have no doubt that other religious traditions have similar words that express the same idea. Right, so back to what we're talking about now. So when we say the ratio of the angle to the sine of the angle opposite, sorry, the ratio of the side of a triangle to the angle opposite. Let me fill out this diagram now by including the lengths of the sides. So in this diagram with the right angle triangle, this side here is 8. Let me leave it as 8 centimeters for now. This here is 6 and this here is 10. Right? That's a multiple of the 3, 4, 5 triangle that we discussed earlier. In this triangle here, this is your acute triangle. This here side here is 6.6. This side here is 6.3. And this side here is 6. And in the obtuse triangle that we have here, this side here is 6. This side here is, it was 8 by? Yeah, this side is 8. And this side here is 12.2. Yeah? Right. So, yeah. So we have 3 triangles. This one we're already familiar with. So you know, for example, and let me stick to sine for now. You know that the sine of 53.1 degrees is 8 over 10. Right? Opposite over hypotenuse. We know that. How do we make that into the sine rule? Well, let us go back into the sine rule again. Right? I have to, well, I'm not really apologizing, but I'll just explain it. I'm going real slow. So the only problem I have is to sit through the whole video. But you will not have the excuse of saying that you were not presented with the material. Let me go again. The law of sines says that the ratio of the length of a side of a triangle to the sine of the angle opposite. So in the case of the right angle triangle, let us start with that. The expression of that in this triangle would be as follows. We would say that 8, I just want to make sure I have it written down here, how I have it written down here, are the 6. Let me start with the 6. 6 over sine 36.9. And that is supposed to be the same thing as 8 over sine 53.1, 5. And that is supposed to be the same thing as 10 over sine 90. Right? The ratio of the side to the sine of the angle opposite the side. Right? And I deliberately starting the explanation by using examples and not using the general triangle, so you could actually see the law in operation, and then we clap back to the general triangle at the end. Right? So if you work out 6 over sine 36.9, you'll get to 1 decimal place. The answer is 10.0. 8 over sine 53.1 to one decimal place, the answer is 10.0. And 10 over sine 90 to one decimal place, the answer is just 10. Right? Exact. Reason being that the sine of 90 is 1. We will see the use of that a little later. Yeah? Of course, with the decimals and the angles now, you'll know that the answers wouldn't be specific. Right? So I think one of these ratios was 9.9999 something and the other one was 10.0 something something. In other words, this angle here is not just 53.1. It is actually, let me check it on the calculator and see. Sine 0.8 is equal to, sorry, sine minus 1, my mistake. Sine minus 1.8 is equal to, the actual value of this angle is 53.13010235. And then, of course, the actual value of this would be 36.86989.765. So when we have 53.1 here and 36.9 there, understand that that is an approximation, which means that when you actually try to do the divisions, you wouldn't get exactly 10 in every case. You'll get 10 to 1, we say 1 decimal place or 1 whole number. However, in the mathematics of it, the relationship holds. Yeah? So 6 over sine 36.9 is 10. 8 over sine 53.1 is 10. And 10 over sine 90 is also 10. That is all the sine rule is, you know. And it works whether the triangle is a right angle triangle, whether the triangle is an acute triangle, whether the triangle is an obtuse triangle, or any other variation thereof. Equilateral triangle, same story. Isosceles triangle, same story. Right isosceles triangle, same story. All right? So let me express it here now. Same story. Right? In this triangle, the sine rule will be applied as follows. 6 over sine 55. 6 over sine 55 is equal to something. 6.6 over sine 65. 6.6 over sine 65 is equal to something. And then 6.3 over sine 60. 6.3 over sine 60 is also equal to something. In this case, you would find when you do the actual maths that you get 7.3 here, 7.3 here, and 7.3 here. Taking into account, of course, the accuracy with respect to the decimal places and so forth. How about our good friend over here, the obtuse triangle? Well, we are applying the ratios as follows again. In this case, we would have 6 over 2 sine 2 points, right? 6 over sine 25.1 is equal to, then you have 8 over sine 34.9 is equal to, and then you have 12.2 over sine 120 is equal to. And in every case, well, when I worked it out, let me just work it over again, just to make sure. I want to be as clinical as possible with this thing. So 12.2 divided by sine 120 is equal to 12.2 divided by sine 120. 12 divided by sine 120 is equal to, boom, 13.85. No, it's 12.2, my mistake. 12.2, you see? Divided by sine 120 bracket is equal to 14.08. Okay, so that is 14.1. 14.1. We have to try and be honest here now, right? 8 over sine 34.9 is equal to 13.98, 13.99. This is 14.08, I think. And, sorry, the 14.0 is here, 12 over, right? 6 over sine 25.1, 6 divided by sine 25.1 brackets is equal to 14.1, right? So you have some variation there, but I want to show you again that the variation here is only a product of the fact that we would have approximated the angles here. This 25.1 and this 34.9. As you can imagine, the angle is a lot more precise than that in terms of the decimal places. So for all intents and purposes, practically speaking, we can say that 6 over sine 25.1 is 14, 8 over sine 34.9 is 14, and 12.2 over sine 120 is also 14. The actual answer might be 13.999 or whatever it is. The point I'm trying to make here is that the sine rule works. That is basically what I'm saying here. So we explain the sine rule and we use 3 specific triangles, right? These are more or less the triangles that you would meet in any exam. You would meet a right angle triangle. You'll meet some version of an acute triangle. And you will also meet some version of an obtuse triangle, right? So I make sure and I use 3 so that you can see in every case that the sine rule actually works, right? So let me now go back to the right angle triangle that we're familiar with and show you how the sine rule works with the right angle triangle. So check this out. So, yeah, now we rub off everything at night. So we're coming down in the corner here. I just want to show you that the thing working, man. Right? What I try to do as much as possible, I don't just give my students the laws. I try to show them the thing in operation. So that when you start to get general, you will be operating with a certain level of conviction. That makes all the difference in the world. So let us say, for example, that, let us say we know from the sine rule, and I'm going to express it a little differently now, that 10, let me say 8 over sine 53.1 is equal to 10. I have to try and squeeze it in here, boy. Even the big board, we crouch for space, you know. 10 over sine 90. Let me use that for now. Right? Right. Remember that sine of 90 is 1. Check it on the calculator and see. So the next line here would be that 8 over sine 53.1 is equal to 10 over 1. And in case you realize it, when you cross and multiply, what you'll actually find here is that 8 over 10 is equal to sine 53.1 degrees. So in other words, this here is what we're already familiar with. We look at this right angle triangle and we say that yes, the sine of 53.1 is 8 over 10, opposite over hypotenuse. What we have not really been aware of up to this point is that this is simply another version of this, which is simply another version of this, right? So the mass that we know so far is just one small corner in the room. So the further we go into it, the deeper we go into it, the more we start to adventure into the room. That is what the maths is about. All right? So it's the same thing. The same thing we're doing all the time. Then we use the next pair now. Let us say, for the sake of argument, that again, and I'm being very specific now, Right? Let us say, for the sake of argument, that we can say that, let me use the 6 now. We can say 6 over sine 36.9 is equal to, again, 10 over sine 90, right? Of course, sine 90 is equal to 1. So therefore, 6 over sine 53, sorry, sine 36.9, sine 36.9 is equal to 10 over 1. Therefore, 6 over 10 is equal to the sine of 36.9 degrees. Right? Again, we're familiar with this. The sine of 36.9, opposite over hypotenuse, 6 over 10. That we already know. That we already know. Right? But again, I'm going through all of this just to demonstrate that the thing that we're already familiar with is part of the thing that we're not so familiar with. So that when we're going into the thing that we're not so familiar with, understand that it's the same thing that we're dealing with. And are taking the step to come back and show you the thing so you can understand the thing. Yeah? Trinilingo now. Yeah? Right. So that basically is it, you know. That basically is it. I trust that now you can check out these ratios for yourself. The actual triangles I got using software on the internet. Right? I think GeoGebra is the name of the software. But you can't just put 3 lines together and drop any length and call it a triangle. Right? You're dealing with angles, you're dealing with lengths. Certain lengths will go with certain angles to make certain triangles. So you have to be very specific. You don't have the luxury of just stringing 3 lines together and calling it a triangle. Right? That is why we get here 12.2, we have 6.6 here, 6.3 here. We have the luxury of doing that with the right angle triangle because we already are aware of the Pythagorean triplets. 3, 4, 5, so this will be 6, 8, and 10. Of course, when we do that, you will realize that we don't have controls of the angles inside. The angles will be decimals. So we're way beyond the point of expecting whole numbers in every single case that we're dealing with. We have to learn to live with decimals. Decimals are part of life. Yeah? So I'm going to close the video now by giving a general expression of the sine rule. And then the next step after this, naturally, would be for you as a student to find questions to do. Maybe find other explanations in other places. Right? But the bottom line is you have to give it time and you have to give it attention. There is no shortcut. There is no fancy method anywhere in the world that, if you really want to understand, will save you from the time that you have to spend. Certain things just take time. There's no shortcut around it. All right? So in a general sense, if we want to say sine rule, and I'm going to take the liberty now of erasing the bottom part of the board. All right? The general expression of the sine rule, which is where most people start, which I didn't do, because I wanted to see the law at work first. And then we get into the general, and then we get into question. Generally speaking, what you will have is, you'll have a triangle. Let me see what color we could use, right? You will see a triangle looking like this. You'll see a triangle. Now, just bear with me here a bit, eh? Right. Right, we're taking the bottom part to explain. So you'll see a triangle looking like this. All right? You'll see A here, B here, and C. So this will be small a, small b, and small c. All right? So this is the convention that we use when we label in a triangle, we label the vertices in capital letters. Whether we use PQR or WXY or ABC or whatever letter, we use capital letters to represent the vertices where you have the angle, and we use the common letters to represent the sides, right? So you have small b to represent this side, and opposite small b, you have big B as the vertex. Similarly, we have small a, the side, opposite big A, the vertex, the angle. And then, of course, here we have small c, the side. Let me try and make the c a little smaller. And then you have big C, the angle. That is the convention that we use when we label in triangles. And this is important. You must be aware of this. Because if you go into a question and you have the side and the angle labeled incorrectly, even if you write down the correct formula, you have problems. Yeah? So the sine rule, based on a triangle looking like this, tells us that A, small a, over the sine of big A is equal to small b over the sine of big B, and that is also equal to small c over the sine of big C. Usually, in working out a question, you wouldn't need more than two of these at one time. So you might have the question set up in such a way that you have to say A over sine A is equal to C over sine C. Or you might have to say A over sine A is equal to B over sine B. Or you might have it set up in a way where you have to say that B over sine B is equal to C over sine C. So even though the general law itself is expressed as an equality of all three ratios, in terms of practically working out the question itself, 99 times out of 100, you wouldn't need more than two at any one time. All right? So that basically is it in terms of explaining the sine rule, in terms of giving you the information. But of course, as with all things mathematical, if you're trying to learn it, that's like learning to play a musical instrument, or learning to drive, or learning to fly an aeroplane, or any other skill that requires any kind of technique. You're an athlete and you're learning sports. You learn to swim. Yeah? You have the information, but you had to work it, you had to practice. So again, I want to encourage you, don't fall for people coming to tell you that you could do it easy and you could do it fast. Right? That is not how this thing works. You have to take time and you have to make time for it. To the extent that you fail to do that, you will have problems with this mathematics. So I hope that the explanation would have provided some level of enlightenment, and I trust that you will take the next step now and work it. Look for problems wherever you find them and work it, whether you're on your own or whether you have somebody working with you. All right? So stay tuned. We're coming up with the cosine rule on the next video in this series.